So what we're going to do here is we're going to continue developing occupancy models. We're going to have a look at what are known as dynamic occupancy models. And basically the only real distinction between what we looked at before, the single season occupancy models and the dynamic occupancy models, is that here we're allowing for psi to change over years. Right, so we imagine we go visit a set of ponds, let's say this year, we go out and visit the same set of ponds next year, same set of ponds in a third year, and we're looking to see the degree to which things related to the proportion occupied, the psi parameter, change over time. Right? So we might imagine that for species that are becoming progressively threatened, that the proportion of available patches that they could live in is decreasing, or for invasive species, the proportion occupied by the invasive species is increasing psi over time, and so on and so forth. So the way we do that is to make use of the robust design. So as we mentioned during the robust design lectures, it's a very useful, very general framework that has lots and lots of applications. And here we simply apply the same framework to multi-season or dynamic occupancy models. We imagine that we have multiple seasons, multiple primary periods. So, different years of our study. Within each of the different seasons, within each of the different years, primary periods, we have these secondary samples where we say we visit all of our ponds, k times. And so within each season, we again imagine that the sampling is closed. So within a season, within a particular year, the true occupancy state is affixed, is a constant because it's closed. But between successive primary periods, between successive seasons, the system's open, and you can have either extinction or colonization events. Extinction being, patches go locally extinct, the species is no longer present. Colonization being patches become colonized, new individuals from a particular species enter a patch. Now, it's important to remember that for a local extinction event to occur, a patch has to be occupied, and for a patch to become colonized, it has to be empty. So for those of you who took 3100, you'll remember perhaps back to that particular set of lectures where we actually talked about extinction and colonization as a function of the current state of the system. Now in 3100, we focus mostly on stability and things related to that. Here, our focus is largely on estimation of parameters. Okay, so here's a diagram which sort of represents the basic sort of sequence. You might have a patch that becomes occupied or is unoccupied. And then in season one, it's in one of two states. It's either occupied or not. And it either stays occupied by not going extinct, so it's the complement to occupied, or it becomes locally extinct. Conversely, a patch that's unoccupied can become colonized, or it can stay not colonized or stay empty, and so on over the multiple seasons. All right, so in order to parameterize this in sort of a useful way, we use psi, again, to indicate the occupancy state for a particular year. So it's subscripted now with the particular season or the particular year. So psi 1 is the probability that a particular unit is occupied in season 1. Epsilon is the probability that it becomes extinct, so becomes unoccupied between seasons t and t plus 1 is epsilon t. And E for epsilon, E for extinction, that's the easy way to remember it. Gamma is the probability it becomes occupied. It's not the same gamma as in a regular robust design model, but it's the one that corresponds to becoming occupied. And then P is the probability of a species being detected in a particular unit given the particular sample in the particular survey sample in a particular season. So if we take the same diagram and we literally just rewrite it now in terms of the parameters, again, we see that we have the psi parameter representing colonization, or it's not the colonization rather, but it's the occupancy state. And if it's occupied, it can either stay occupied, 1 minus extinction, or it can become extinct. Similarly, if the patch is empty, it can become colonized, probability gamma, or it can stay empty, probability 1 minus gamma. Okay, and that's the basic probability structure that we're interested in looking at. The probability expressions themselves, again, the thing that we need to keep in mind here is that for the within season sampling, the population's closed. Between season, it's open. And so what we invariably end up having to focus in on is how do you explain the 0, zeros? So what does a 0, 0 represent? Well, a 0, 0 could represent the fact that the patch is not occupied at all. It can be completely empty. And if a patch is empty, then the probability of detecting anything is obviously 0. Or it can be occupied and, in fact, you just don't detect it. And the thing that we have to do here, and the only real complication is if you look at the first season, the patch is occupied. If you look at the third season, the patch is occupied. So our probability expression has to account for the pathways by which you could get the 0, 0. And let's run through that, and I think it'll be clearer if we actually run through it. So here we are in the first season. It's occupied. We detected the probability on the first occasion, 1, 1, and we don't detect it on the second, so it's 1 minus p, 1, 2. So again, 1 is the season, and then 2 is the sample within the season. And so detected, and then missed. And then we get into the more complicated ones. So all you need to do is sort of mentally run through the two different ways that you could get a 0, 0. It could be that it went extinct, and which point that you just don't see it at all. Or it could be that it doesn't go extinct and you just missed it. So let's start with the latter. It doesn't go extinct. So what's the probability of it not going extinct? Well, epsilon is the probability of it going extinct. So 1 minus that is the probability that it stayed occupied. So one possibility is it stays occupied with probability 1 minus epsilon, and then you miss it the first time, and then you miss it the second time. And then we have this extra term here. Why? We have this extra term because we have to account for the fact that it goes back, or excuse me, that it stays occupied. Okay, so here we are in the first season, and it's occupied. It stays there with probability 1 minus epsilon. You miss it twice, and then it stays there between the second and the third seasons with probability 1 minus epsilon 2. So that's one possibility, that in fact it's still occupied, but you just missed it. What's the other possibility? Well, the other possibility is it goes extinct, and then you don't see anything because it's extinct, and that should hopefully make a certain amount of sense. So this is what's being represented here. You're occupied in the first season. You go extinct with probability epsilon 1, and if you're extinct, you're not detected at all. So there's no p parameters that we need. And then between 2 and 3, you become recolonized again, and that's with probability gamma. Okay, so those are the four, those are the two expressions that correspond to the 0, 0. And now we're into the third season, 1, 1. Well, there it is, 1, 1, you detected it. It stays colonized, and then you miss it on the first sample of the fourth year, and then you see it again. All right, so this is a little bit more complicated than the probability expressions that we've seen previously, but hopefully not too much so. And if you sort of step through it, replay this part of the video or read the material in chapter 21, I think you'll see it. Okay, so once we've got our probability expressions going, then we simply generate our likelihood expression, our multinomial likelihood, just as we have with everything else. We let Mark do all the optimization, and away we go. Now, as far as covariates are concerned, because we have more parameters, we have psi and epsilon, gamma, and p, we can do more things with it. We can have season-specific covariates. We can have them constant. They have to be constant within a season, but we could allow them to vary between seasons, like habitat patch or some measure of patch isolation. We can also have survey-specific covariates. Okay, so we can model P, and they can vary between the surveys, and they can reflect, local conditions. So I think it's still sort of easy to remember the distinction between season and specific, or survey-specific. Survey is kind of like individual covariates, and season-specific has to do with these environmental ones that go from there. Okay. Well, I'm not sure that's actually right. Let me think about that for a second. Yeah, so survey-specific is environmental conditions that, yeah, okay, I'm right, never mind. It's been a long day. Okay, so what do we want to do with this? Well, we want to estimate occupancy. Now, occupancy, if we go back here to the expression, is not actually a parameter in the likelihood in the general sense. It is a parameter at the beginning, because what we're doing is we're following the system from some starting point through time. So we look at how does psi change given the probability of extinction or the probability of colonization. So what do we do here? Well, because psi only shows up at the beginning, then all of the subsequent psi's have to be calculated by algebra. All right, so if you knew what the psi was at the beginning of the season, so it's, let's say, time t, and I tell you what epsilon is and I tell you what gamma is, then I can tell you what psi would be next time step. So if you look at this for a second, you should see that. So if psi was 0.5 and epsilon was 0.2, then the probability of it going from occupied and staying occupied is such and such. Similarly, if it was empty, we can say what the probability is of becoming colonized with gamma. Now, there are other parameterizations that can be used. You could parameterize this whole thing just in terms of psi at each time step and epsilon, but no gamma. You could use psi at each time step, but no epsilon, but just gamma. So this is analogous to the Pradel models, where you may recall for Pradel models, there were Pradel models that had lambda and either recruitment or lambda and survival in the likelihood. That's motivated largely by this desire to think about modeling psi directly as a function of covariates. But most of the folks who work with this stuff think that's kind of silly for the same reasons that it was silly in the Pradel model, because you impose a covariance structure on things that we're not interested in. So the model that you really want to use is this one, where each successive lambda each successive psi is a function of the preceding psi and then modified by the estimates for epsilon and gamma respectively. Just like in the Pradel model, psi, or lambda rather, was a derived parameter given that you know something about survival and recruitment. Okay, so what are we interested in with respect to psi? Well, we'd like to look at how it changes. And so there's a couple of ways you could do this. If this wasn't psi, if this was n, then the natural thing to think about is having n at t plus 1 divided by n at t. That's how we define lambda. And we could do the same thing with psi in principle, except we have to remember something. Psi is a proportion. It's a number that's bounded from 0 to 1. And so you can get really weird values for lambda, which make no sense, including a lambda of 0, which absolutely doesn't make any sense. So because of that, even though this is in Mark, it's not particularly satisfactory. And folks like Daryl McKenzie and Larissa Bailey have kind of concocted an alternative approach, which is based upon something called log odds, where lambda, and it's called lambda star, is represented as you see here. So if you look at the numerator, this is basically like the logit. It's the log of the odds. So it's psi divided by 1 minus psi at time t plus 1, and then the denominator is the same thing for time t. And this tends to be what most people are using at this point, is looking at variation in this lambda star parameter. Okay, so the standard assumptions for the dynamic occupancy model, again, closure within seasons, and that all the colonization and extinction occurs between seasons, but not during the season. So, individual ponds don't change. They don't go locally extinct or become colonized during the year, but between years, that's fine. Surveys are independent. All the sites are independent with respect to the dynamics. And again, there's no unmodeled heterogeneity. So to introduce this, we're going to look at some data from the Blue Ridge salamander study. This was part of Larissa Bailey's PhD thesis, and I suppose in deference to Larissa, I should acknowledge that this was absolutely, and I'm pretty sure, the very first example of the application of dynamic occupancy models to a real-world situation. And so we're going to look at a little piece of it here. So we're going to hop out of PowerPoint and go into Mark. The Blue Ridge data, you'll find it in markdata.zip. It's called blueridgesalamander.inp. If we look at it, there's some basic information. These were 4 years of data from her PhD work, 1998 through 2001, 5 surveys per year. The number of occasions are 20. Now remember, this is a robust design style thing, so we have 20 total occasions. we are split amongst the 4 years, 5 surveys per year, so 4 times 5 is 20, so we need to telemark that when we fire this up. There's some information about some of the surveys. There's one covariate, and that's the height of the sample, or the site rather, elevation. These are in the Blue Ridge Mountains. And there were 2 groups, and she was particularly interested for dissertation work about occupancy as a function of the proximity of the site to a stream. So group 1, there was a stream nearby the sites that she was looking at within less than 50 meters. And in group 2, the stream was further away. So wet sites, dry sites, however you want to phrase it. Okay, so there we are, 20 total occasions, 4 primaries, 5 secondaries per primary. I'm going to go ahead and start mark here. And we'll look at some of these analyses. Pretty straightforward stuff, given what we're going to do here. Again, this is all talked about in the chapter, and this is later on in the chapter where we start dealing with multi-season occupancy, but we'll look at the basic stuff to begin with. Okay, so here we have occupancy estimation, but now we're dealing with multiple states. We're not just dealing with a simple single state model. We have to actually telemark that we have multiple years. It's not the most complicated thing in the world, but we do need to say that that's what we're going to do. And so if you run through the list here, again, there's the single season stuff. And now what we're going to look at is multi-state occupancy. And then you'll see there's correlated detections, relaxed closures. There's all sorts of clever things that you can do down here. But we have one particular thing that we want to do, and that's the multiple state occupancy estimation. Click OK. Okay, so we fire up mark here, and what we're going to do then is we want to look for occupancy. Now, earlier we used occupancy estimation down here. That's for single season work. We need to use the robust design occupancy to account for the fact that we're dealing with multiple seasons. So we'll click that, and here you'll see some of the models that you can build. There's a lot of them. The one we're going to work with, for the reasons I mentioned a moment ago, is robust design occupancy. We're going to estimate the first psi and then calculate the subsequent psis as derived parameters. And then psi1, gamma, and epsilon will be in the likelihood, so they can be modeled in the design matrix. So that's what we'll click. These are the Blue Ridge salamander data. We're going to go ahead and grab the file, blueridgesalamander.inp. We have 20 total occasions. We use easy, robust design times to set things up. We have 4 primary occasions. Each year we had 5 samples. Click OK. How many covariates do we have? Well, we really only have the one covariate, and that's the elevation. So I will just do ELEV for elevation. But we have 2 groups. Okay, so we have to remember what the 2 groups are. If we look at the file, the first group is near stream, and the second group is the stream is further away. So that's what I'm going to call them. My group labels are going to be near and far. Click OK, and then we're ready to go. And hopefully you're following along fairly well. Okay, so click OK, and start us up. We look at our PIM chart, and it's relatively busy. There's a fair amount of stuff in there that we need to keep track of. But again, the basic ideas are pretty straightforward. Some of these things we're going to collapse down for different models that we're interested in, and so on and so forth. So just to give you, a little bit of a hand here, just manipulating all these things, let's go ahead and make all the P's for the different primaries, just make them all constant. Okay, we'll allow them to differ between sites, and we'll allow them to differ between seasons within a site, but let's just make them all constant. So just as a trick, again, there's lots of things. You can right-click each of them and make them constant, or if you hold down the Shift key and then you select those 4, or excuse me, not 4, I guess there's 1, 2, 3, 8 boxes. Now they turn all lime green, and we can make all of those constant, and we're done in one shot. Renumber with overlap, and that just sort of simplifies things a little bit for our purposes. Okay, so what do we got here? Well, we've got psi for the near sites, so near stream, psi for the sites where the stream is further away, epsilon near, epsilon far, gamma near, gamma far. And to some degree, I could say, man, you guys should probably be able to figure this out already, but let's just go ahead and run this. So this is going to be my kind of starting model. So this is going to be just our psi model with a group effect. So I'll just call it G for group. Okay, what's my next parameter? Well, my next parameters are epsilon, so I'll just use EPS for epsilon, and it's going to be group by time. Okay, and then I've got gamma, which is not only GAM, so I don't confuse it with group. So gamma is group by time, and then I've just got my P parameter. So the only thing I'm going to fool around with just to demonstrate here are epsilons and gammas. So and this is going to be the one that I run with the PIM, and you know what's coming next. So let me just add PIM here to the name of the model. Click OK to run, and there we are. So let's just look at our results for the moment. There's the psi parameter for near the stream, and there's the psi parameter for further away from the stream. Here's the epsilons, and again, how many epsilons are you going to have? Well, you got 4 seasons, so you have 3 intervals. But of course, for fully time-dependent models, we need to think about possibilities for confounding or just poor estimation. And we see we've got some problems going on here, but there they are. Okay. Mostly I want to show you the design matrix for this. And again, this is really no more difficult than anything you've seen before. We just have to apply the same technologies to more parameters. All right, so what's the design matrix going to look like? Well, I can't do the full because I made the detection probability is all constant. So I'll do reduced. There's 22 columns. That's not too bad. So let's go ahead and build our design matrix that corresponds to that. I have a psi parameter separately for each of my 2 different locations. Okay, so if we want, I can do this will be psi for near, and this will be psi for far. And then I've got epsilon, and there's nothing here particularly that I might be interested in setting epsilon and gamma equal to each other, so I'll treat them as separate parameters, but I do have 2 groups. So I have an intercept for epsilon, and then near and far. So let me label these. I want to do the right thing here. So this is going to be my epsilon intercept, and this is going to be my group. Okay, so near and far. And then I have my time intervals, nothing new here, in fact, exactly the same as you've seen before. And then we're going to have our interactions, so it would look like this. So if I go ahead and label all these, appearance, label columns. So this is going to be my G, or excuse me, my T1, T2, and then it's just G times T1. And then G, oops, one too many there, G times T2. I'll clean that up, and let's have a look at our design matrix. I'll make it a little bit bigger so you can see it better at home or wherever you happen to be. Okay, so we do exactly the same thing for our gammas. Okay, so there's our intercept, groups, time. Let me move this over, get it out of the way here. So here's our time, and then our interaction. And I'll add some columns. Or labels rather. So this is going to be my gamma intercept, my group, my time 1, time 2, G times time 1, G times time 2, so on and so forth. And there we are. And then I have to put in my detection parameters. I'm not doing anything fancy there, so I'll just proceed and use the identity matrix approach, which we've used before. I made a mistake. That's because I didn't move that bar over. So let me just fix this up. I got out of sequence there a little bit, and there's a way to solve that. I'll just move this over so I can have a better idea of what I'm doing. Always a good idea to know what you're doing. And there we go. So it's just 1, 2, oops, and there we are. Okay. So unless I made a typo somewhere, this should be exactly equivalent to the one that we just did with the PIMs. So this will be my design matrix version. Click OK, run it, and away we go. And we get, oh, something not exactly right. Let's see if we can figure out why. Huh. Let me look. Let me look at my PIM again to begin with. Let me look at my PIM chart. Let's see. I'll make this this far. I got 22 parameters there, and in my design matrix one, my design matrix has 22 columns, but I'm not getting 22 parameters. So let's go and look at it. Now, here's my suspicion. I'm going to rerun the PIM one, but I'm going to use the logit link. And I run the logit link one, and yeah, there it is. We clearly are having some problems. We know we should have 22 parameters. So if I change the number of parameters to 22, then they're the same. And if I go up here and I do the same thing, I should get basically identical or near identical everything else. Now, I still get a slight difference here with the likelihood. So let me go ahead and just have a quick look. And I'm doing this partly because I want to point out that, you know, some of these parameters are just not going to be estimable because of the same kind of problems that we had before. All right. Fully time-dependent models, you have some problems with identifiability for some of the gammas and so on and so forth. So a fully time-dependent model is not necessarily a really good one to start with. And that's why we're getting small differences in the likelihood, but they carry over into the AIC differences. More typically what we're going to do, and I'll just pull this model up, is we're going to fit them as functions of parameters that we might be interested in. So for example, we might think that psi is going to be a function of the elevation. So how could we do that? Well, one thing that we could do is we could build a model which allows for psi to differ as a function of whether you're near or far and elevation. So how could we do that? Well, I'll make a model that has an intercept for psi. So this is going to be my psi intercept. So let me relabel this. This is my psi intercept. Click OK. This is my group, my location, so I'll label that. Okay, so this is my group. And I'll make the near one a 0, and then the far one a 1, doesn't really matter. But now I'll put my covariates in. And what are my covariates? Well, ELEV is my elevation covariate. ELEV, and I could make it, I could have an interaction, but I'll just leave it at this. So this is an additive effective elevation. I could do something similar over here. I could do this. I could have ELEV for my epsilon. So maybe the extinction probability is a function of that. I can copy the value down, let's see, 6 times. There it is. Could get rid of my time columns, so 7 through 9. Delete multiple columns, 7 through 9. And I could, now let's build a model where I just have a group effect on gamma, but no time effect. So I'll get rid of 9 through 12, and so on and so forth. So really, you know, there's nothing particularly new here. So I'll just build a couple of models, and I'll show you a few things that we might be interested in. So there we are. I run this model, and this is a model where psi is a function of group plus elevation. I have the epsilon parameter is a function of my group plus elevation. So I didn't build an interaction, but I could have. And then I'm going to have my gamma as a function of just group, and so on and so forth. So, you know, some model that we might fill it. We add it and we run it to the browser. It does really well. If you read through chapter 21, you'll see much more discussion about this and why this makes sense. Okay, so some models that we fit, fully time-dependent models, are going to have all sorts of problems, but they're the starting point. And then what do we see? Well, we see our estimates. These are our psi parameters, our estimates of epsilon and gamma respectively. And where are those lambda parameters? So we go back to this diagram or to the PowerPoint. Where are these different lambda values? And where are the psi parameters that we're interested in? So what is this psi that we get here? And this is kind of important. This psi, let's look at those numbers, 0.974, 0.849. Now let's look at our derived parameters. 0.974, 0.849, those psis are the first ones, okay? Those are the psis that were estimated for the very first season. Here are the psis for season 2, 3, 4, 2, 3, 4 for the near and the far locations. Where do they come from? They come from taking the psi from the first season, and then with the estimates for epsilon and gamma, calculating psi for t plus 1. And then you do it again. You put psi t plus 1 in here, take the epsilons for that season, and get psi t plus 2, and so on. Okay, so you're just extrapolating or projecting out. So in our output, that's where these psi values come from. Okay, that's estimated in the likelihood, that's estimated in the likelihood, but the rest of them are derived parameters. And here are the lambda parameters. So here for the near and the far, here for the near and the far. This is the lambda, and then this lambda star, or here it's called lambda prime, because I guess Gary decided to call it lambda prime for some reason in Mark, but you see the different values that we have. Now, interpreting them in some senses is easy. Increasing or decreasing is relatively straightforward, but the actual magnitude of those things will make sense only if you go back here and remember what these are. So psi is the probability or proportion occupied. So this is the ratio of those proportions. So what does that actually mean? And here's the ratio of what are known as the log odds. And again, you're going to have to think a little bit about how to interpret these things in terms of what the actual magnitude means. What is relatively straightforward, though, is the notion of increasing or decreasing over time. So if we look, for example, at the sites that are further away from the stream, you can see that either lambda or lambda prime or lambda star, whatever you want to call it, are both increasing, whereas near the stream, there's no real change. Okay? I mean, arguably, maybe a little bit of a bouncing around, whereas when you use lambda prime, and this is something to think about, and I'm going to have to ask Larissa about this, here, when we're looking at near, the change is pretty small, but here the change is pretty dramatic. They're both increasing, but the magnitude of the increase differs very much between using lambda or lambda prime. So I'm going to have to look into that, and I'll see if I can get back to you on that. Okay, so multi-season occupancy models, the main focus is on the change in psi and whether that change is more sensitive to extinctions or colonizations. A lot of this should be familiar to you if you remember anything at all about the lecture that we did this in 3100. And if you don't have those lectures, I'll make those available somewhere for you to look at. Okay, so these are the dynamic occupancy models. Now, there's a huge amount more that you can do. And again, if you simply start something new, you'll notice there's occupancy models all over the place. Multi-species occupancy models for looking at two species and how they interact, et cetera, et cetera, et cetera. And all of these different things here, false positives, multi-scale for if you have different kind of detection devices. Again, there's so many different occupancy models, and they're becoming produced so quickly that it's very difficult to keep up. Now, in the Mark book, chapter 21 is on what we've talked about. It's on the single season closed occupancy models and on the multi-season open occupancy models. But a lot of the other things that are out there aren't discussed. There is a chapter in the Mark book, chapter 22, which talks about multi-species things. So if you really imagine there's species interactions like the barred owl and the spotted owl, that would be the more robust, more modern way to do it. And that's chapter 22. And at the moment, there are several more chapters being written as we speak. They're not in the book yet, and you're clearly not responsible for them since they don't exist yet. And for the reasons that I mentioned in the first part of this lecture, we're not going to look at the multi-species stuff, chapter 22. We're simply running out of time. But if you sort of follow along what we've done, really work your way through chapter 21, then you'll be in good shape. And then you get a copy of Daryl's book, the second edition of the occupancy book, and that will tell you all the really new, very cool things that you can do here with occupancy. So watch this lecture, watch the one that went before it, and absolutely watch Gary's lecture on this. You'll get some different insights and perspectives from Gary, and hopefully the combination of the two will set you up pretty well. All right, take care. Thanks, everybody.